In the last video we looked at how simple linear regression fits into the framework of a linear model, and in this video we're going to see how analysis of variance also fits into that same linear model framework. So we'll revisit an example we looked at before. So this was to do with circadian rhythms, and we have a predictor variable, a treatment variable that has 3 levels, and so I'm going to turn it into a factor so that I can order the levels as control and then knee and then eyes. And then, just as in the last video, I'm going to first fit a null or reduced model, and same kind of thing as before. I've got my response variable here, and then on the right hand side of the tilde I'm specifying no predictor variables. I'm just specifying one, which means all I'm going to do is fit an intercept term to the model. And then I'm going to draw a picture of the data and a line representing that null model. So here we can see the response variable is the shift in circadian rhythm in hours, and my predictor variable is on the horizontal axis. I've got the light treatment with 3 levels: control, knee, and eyes, and we can see the data points here. And then this horizontal line here represents the null model if I ignore the treatment level. So that means I would predict the shift in circadian rhythm to just be the same regardless of the treatment, and that prediction would be set at the average of all of the response variable measurements, ignoring the treatment. By contrast, my full model will have the treatment as the predictor variable. And then now if I draw the same kind of graph, instead of having the same prediction regardless of treatment, I'm going to have a different prediction whether the treatment is control, knee, or eyes. So this is a representation of that model. So when the light treatment is the control, this is what my predicted circadian rhythm, shift in circadian rhythm is. If the light treatment is knee, this is my predicted shift in circadian rhythm, and if the treatment is eyes, this is my prediction of the shift in circadian rhythm. So just as in the last video, what I want to do now is I want to consider what is the improvement in fit from here to here. How much better does this model represent the patterns in the data than this model? So I'm going to look at an f-test of the improvement in fit, which, just as in the last video, we can obtain by using the ANOVA function. So we're doing a hypothesis test here, so I'm going to lay out my 4 steps. My first step is to state the null and the alternative hypotheses. Null hypothesis is that the treatment means are all the same, so that would correspond to this model. Treatment means are all the same. And the alternative hypothesis is that the treatment means are not all the same, so that would correspond to this model. The next step is to find the test statistic, so it's given here by this F statistic in the ANOVA table. Third step is to find the p-value, so that's the p-value also in the ANOVA table. And then step 4 is to make a decision, draw a conclusion. So I'm going to reject the null hypothesis in favor of the alternative because this p-value is smaller than my significance level 0.05. And so my conclusion is that the treatment means are not all the same. So now that we've determined that this model does represent a significant improvement in fit over this model, I can use this model to make predictions. So in this case, there's 3 predictions I'm interested in making. One is the shift in circadian rhythm for patients who have the control treatment, and then I want to predict the response variable for patients with the knee treatment, and then finally I want to predict the response variable for patients with the eyes treatment. So how can I do that? Well, I can kind of eyeball it from the graph, but if I want to be a little more precise, which I do, then I need to run this function here, the summary function. So if I run the summary function, I get this table of coefficients, and I'm going to use these estimates to make my predictions. So you can see that I have an estimate for the intercept, and I have an estimate for what R is calling treatment knee, and then I have an estimate for what R is calling treatment eyes. So the level of the treatment that's left out, which is control in this case, that's known as the reference level. And then this predictor variable here represents the difference between knee and the reference level. So it's the difference between knee and control. And then this one that says treatment eyes is going to be the difference between the eyes treatment and control. So how does that all work? So perhaps easiest to actually do the calculations so you can see how this all works. So if I'm going to predict control, that's the reference level, all I need to do is I need to pick off the intercept term. So minus 0.30875. So that's the predicted shift in circadian rhythm for patients undergoing the control treatment. If I want to predict the patients, the response variable for the patients undergoing the knee treatment, I have to add the intercept term and the estimate that goes with treatment knee. So if I do that, I get minus 0.33571. Okay, so the predicted shift in circadian rhythm for patients undergoing the knee treatment is minus 0.33571. It's not all that different to the prediction for the control level, and we can see that in the graph. It's just a little bit lower, a little bit more negative. Finally, for the eyes treatment, I'm going to add the intercept term and the term for the eyes treatment. And so if I do that, I get minus 1.55. Okay, so for the eyes treatment, this is much more negative, much lower on the graph than these other two levels. So there's a bigger negative shift in the circadian rhythm for people having the light shone in their eyes, as opposed to people having the light shone on the back of their knees and people who don't have a light shone anywhere. So that's if you're doing the calculations by hand, and this is useful. It's a useful exercise to go through because it gives you a sense of what these numbers mean in this coefficients table, these estimates here. If we want to do the predictions using the predict function, then we can just use this piece of code here, and we get these results done for you. So no chance of making any errors there, unless you make a coding error. But these three numbers are the numbers that we just calculated here. So that's how we can put the analysis of variance table, the analysis of variance model that we looked at before, into the framework of linear models. And in the next video, we're going to look at a slightly more complicated experimental design and see how we can analyze that in this linear model framework.